Okay, good morning, lads and ladies. Welcome back to differential equations. Give me just 1 second. We're almost set to go here. My wife just gave me a call. She's a little late coming back from the dog park, so I'm still on baby duty. Just 10 seconds. Yes, that's the things so that you keep doing what you're doing. Okay, he is still asleep, so I'm going to try to speak a little bit quietly to keep things from getting out of hand here. Today is going to be our final day working with the Laplace transform, so I'm sure some of you are quite happy about that. Some of the things I'm going to show you today are a little bit challenging, but not overwhelmingly so, and the big goal is to handle those cases. Remember we said that, with partial fractions, there are some cases where you output stuff that doesn't look like things we know the inverse Laplace transform of. For example, you can have repeated roots downstairs, and that leads to terms like 1 over s minus 1 cubed or s minus 1 squared. And we don't know, how to take the inverse Laplace transform of something like that yet. I'm going to give you a rule that'll allow us to deal with that. One of the other things I'm going to show you is a very important result on something called the convolution of two functions, which is kind of an interesting way to get like products of Laplace transforms out. But it's a little bit of a weird thing. So it's not what you would think, right? The Laplace transform of a product is not the product of the Laplace transform. But there is something that gives you the product of Laplace transforms, and that's called the convolution of two functions. Another little note, there is some material that I would like to cover that we're, I think, not going to cover in the interest of using time well. And because it would require a rather large amount of background, discussion of the Dirac delta function is going to be omitted here. And that definitely does make me sad. But unit impulse and Dirac delta functions, they're very important in applications, but they require pretty substantial discussion of distributions or things that aren't quite functions. So I'll show you what they are very briefly, but I've gone through your homework and removed those problems from the homework set. So while I will show them to you, I will not be requiring you to solve associated problems in the homework, and I won't be testing you on them. Okay. A few other little kind of notes about the course. Get started here. This is MAP2302, which is differential equations. It's a lecture. Oh, and it's no longer July, is it? It's the 2nd of August. Okay, so today we're going to cover what are called operational properties of the Laplace transform. And there's a few sections here. It's going to be like 7.3, 7.4, and 7.5, but we're not going to cover all of it, right? Just a few little bits of each. When I learned about Laplace transforms, these were all boom, boom, boom in one section. Your book splits them up into multiple sections. I don't know why, but they do. So that's the main topic for today. A few little announcements. Of course, everything I said about the Dirac delta and unit impulse functions there, you don't need to know that. That doesn't need to be in your notes, right? Just like it's something that you're not going to be made to do. But there is another kind of relevant announcement, and that's that your third test, I'm going to use a take-home test, exam 3. So there will be an associated honor pledge. The questions will be written in such a way that they're not things that you could easily cheat on. But of course, I'll be looking very, very carefully at your responses here to make sure that they are your own. You can't work with other people on this. And I will be giving this out on Thursday. It will be due at the start of the final. So those of you who've taken classes with me in the past where we've done these, it's not terribly uncommon for me to do the last exam in a course like this as a take home. It's going to work like that. So it's going to be a PDF that I will post to Canvas. You'll all download, print the PDF, write in your answers, you'll sign a little honor pledge, and then you'll scan and submit the completed test before beginning the final exam. Okay. I think that's it. Yeah, so today is our last day talking about the Laplace transform. And then tomorrow and for the rest of the course, we're going to be talking about power series solutions to differential equations, which I think is the reason I'm doing the take home is to make sure that you guys have a chance to sort of understand the power series stuff. I don't want to rush it. So let's go ahead and get into the stuff for today. Oh, your last two homeworks are up. I posted those actually last week. Like I said, I modified one of them, the extra Laplace transform homework. I yanked some problems out of this morning, but I don't think anybody had gotten to those yet, so I'm not stressed about it. When we say, well, let me, so this is section 7.3, which is titled Operational Properties. So all of your tests are graded. If you haven't seen that yet, of course, the exam 2 grades, finished all those yesterday. Please take a look at the comments that I wrote on your written work, and also take a look at comments that are under the individual questions within the test itself. So yeah, this section is titled Operational Properties 1. The big deal here is something called like an exponential shift rule, and kind of the big idea that we know that partial fractions run on, say, y of s equals some rational function of s can output terms like some constant over s minus a, or some constant over s squared plus a squared, or some constant over things like s minus a all squared, or things like some constant over s minus a squared plus k. We really only know how to handle these first two. I should say maybe it's like bs over s squared plus a squared. So these guys we know how to handle. Right? These are basic exponentials. These are like sines. These are like cosines. But things like this, we really don't know how to handle. And this guy, you could have something like c over s minus a cubed, and so on. Right? So repeated roots, or repeated factors downstairs, yield things like this. And then certain quadratics, you complete the square, and you remember back in your Calc 2 class when you would use partial fractions to integrate, you split up your function, you get some sort of irreducible quadratic, but maybe it doesn't look just like this. I mean, instead of like x squared plus 1, you had to complete the square and then do a little substitution, and then you'd get your inverse tangent or further trig sub work. So in order to handle stuff like this and stuff like this, what we need is a rule called the exponential shift theorem, or your book calls it the first translation theorem. So let me go ahead and show you what that looks like. I did look over the CIQ and exam wrapper, and I saw that pretty uniformly you guys are not super into the proofs. So I'm going to try to keep the proofs very simple. Try to keep the discussion of the theory fairly simple. This theorem I will prove. So to handle these, this theorem. And I've always known this as the exponential shift theorem, but your book calls it the first translation theorem. What it really just says is if f of s is the Laplace transform of little f of t, then the Laplace transform of an exponential, say e to the as, or wait, e to the at, sorry, times little f of t is the Laplace transform of little f of s here, but shifted to the right by a units. So that's f of s minus a. So you remember from your pre-calculus classes, what happens if you like subtract a number on the inside of a function, right? Like if I take the graph of x squared and I compare that to the graph of x minus 3 squared, the x minus 3 squared is the same graph, just shifted to the right by 3 units. So f of s minus a is the same function as f of s, just shifted to the right by a units. And sort of what this theorem says is that if you multiply your original little f by some exponential e to the at, then you'll get more or less the same Laplace transform, just with the s's all swapped for s minus a's. And the proof here is very straightforward. So I am going to do this proof, but I will try to do fewer proofs and theory discussion in the remainder of the course. I would encourage us to begin by looking at f of s minus a. So instead of the normal definition of the Laplace transform, you could begin by looking at this also. Instead of the normal definition of the Laplace transform, which is little f of t times e to the negative st, this would be little f of t times e to the negative s minus a times t. So remember the definition of the Laplace transform. It's the integral from 0 to infinity, f of t times e to the minus st. So I'm going to swap s for s minus a, thinking of that as a little shift where we just swap the one variable for the variable minus that constant. Then I distribute this negative. So I get f of t times e to the negative s plus a times t dt. And then I distribute the t. And I split up the exponential. So this would be f of t times e to the negative st times e to the at. And then that can be written as integral 0 to infinity, dt. So that is f of t times e to the at times e to the negative st dt. And so if you look at this piece right here, here's your kernel, e to the negative st. So this integral is the Laplace transform of the orange underlined piece. This is the Laplace transform of f of t times e to the at. And that's it, that's the proof. And no doubt you're wondering, how am I going to use this to solve differential equations. How is this going to help me, solve differential equations? Well, the answer is those kind of weird partial fractions things above, like, constant over, say just 1 over s minus 1 squared. That is a shifted version of the Laplace transform of a power function. So let's look at some examples, yeah? We can look at a forward example. So if I want to find the Laplace transform of, say, e to the 5t times t cubed. Certainly one way I could approach this is to just write down the definition of this Laplace transform, right? It's the integral of this stuff times e to the negative st dt. But then you would need to run integration by parts 3 times to knock the power of t down. It's a tedious thing to do. It's not a pleasant calculation. So if we can somehow lean on this theorem, then that will help us a lot. And what we see is that the thing you're taking the Laplace transform of here, e to the 5t times t cubed, fits beautifully into this framework. So here, a is 5, and little f of t is t cubed. I would say the first thing you want to do is recall the Laplace transform of t cubed itself. And again, you could write down the integral using the definition, but this is something that we should know. Right? We found the Laplace transform of t to the n in general. Anybody remember what the Laplace transform of t to the n is?
Factorial over s to the n minus 1. S plus n plus 1.
Yes, very close. Yeah, good. So this is going to be 3 factorial over s to the 3 plus 1. 3 factorial is 3 times 2 times 1, that's 6. Over s to the 3 plus 1 is s to the 4. So if it was just t cubed that I was transforming, I would get 6 over s to the 4. Therefore, by the theorem, by the exponential shift theorem, the Laplace transform of e to the 5t times t cubed should be this thing, but with s swapped for s minus a, which is 5. So it would be 6 over s minus 5 to the 4. And that's it, you're done. So you can get new Laplace transforms, right? New Laplace transform. Laplace transform of some function. If you know the Laplace transform of little f, then you can get the Laplace transform of an exponential times little f just by shifting the Laplace transform. Let me try to make this a little more clear. This is the s. Sorry for the s's and the 5s. Okay, this is a 5 here. So the real place this is helpful, of course, is when you're calculating inverse Laplace transforms. We know that when you run so you have your initial value problem, you take the Laplace transform on both sides, you solve for y of s, you get a rational function of s. It's possible that the denominator there has a term like this, right? Or maybe several terms like this. If you had a term like this, then you could have s minus 5, s minus 5 squared, s minus 5 cubed, s minus 5 to the 4, all stuff like that. That means that now we can take the inverse Laplace transform of that stuff. So this is a big deal. This is something that we've needed. The examples from last week were chosen very carefully to avoid that sort of thing. Let me do one more example kind of in the forward direction, then we'll look at a couple inverse problems, and then we'll solve the differential equation. So let's find the Laplace transform of e to the negative 2t times the cosine of 4t. And as we did before, I'm going to identify a and f of t. So a comes from this exponential here. A is negative 2. And f of t, little f of t, is cos 4t. And then we have to, just like in the last example, we have to recall what the Laplace transform of that basic function is, the one that's getting multiplied. So now here we need to recall the Laplace transform of the cosine of 4t. And then I will take that Laplace transform and shift it to get the Laplace transform we're after. So what is the transform of cos 4t? Does anybody remember that one?
Would be s over s squared plus 16.
Very good. Very good. So the Laplace transform of cos kt, or cos, I'm not going to use a here because we're already using a, cos kt is s over s squared plus k squared. So this Laplace transform is s over s squared plus 4 squared, which is 16. Hence, therefore, thus, by the theorem, the Laplace transform of e to the negative 2t times the cosine of 4t is going to be this guy, but with the s's swapped for what?
+2.
Very good. Yeah, it's like we're shifting to the left now rather than to the right because a is negative 2. So this is going to be s plus 2 over s plus 2 quantity squared plus 16. And hopefully you see that this really does kind of broaden the collection of things that we can take inverse Laplace transforms of. So s plus 2 over s plus 2 squared plus 16. So if I can take inverse Laplace transforms of stuff that looks like this, and inverse Laplace transforms of stuff that looks like this, then I can take inverse Laplace transforms of pretty much anything that can come out of partial fractions. There's one thing here that's not covered by this, and that's repeated irreducible quadratic factors. That will be covered by the convolution theorem. Okay. Let's look at an inverse problem. All right, so we're going to take this same rule and apply it to find the inverse Laplace transform. Stash this aside so I can refer back to it. Another thing that people said in the CIQ is that we want to see more examples, and that the class is so short that it's frustrating, and I agree with you. So what I'm going to do is I'm going to omit some steps that I trust you guys to manage on your own if you need all the details. And I'm going to kind of jump from the function that we're taking the inverse Laplace transform of. Let you handle the partial fractions. I'll give you the result. If you want the details, you can do it. That way we get to see a few more. So let's find the inverse Laplace transform of the following. 2s plus 5, and my s's I'll put tails on like that when there's a 5 around, divided by s minus 3 quantity squared. So the PFD, the partial fraction decomposition on my f of s inside there, is going to tell me that 2s plus 5 over s minus 3 quantity squared can be written as 2 over s minus 3 plus 11 over s minus 3 quantity squared. That's the result. I'll say this, you need to make sure you remember how to do partial fractions with repeated roots downstairs, with higher multiplicity factors downstairs. The setup is, because this is a square, you would have like a over s minus 3 plus b over s minus 3 squared, and then solve for a and b the normal way. The heaviside trick won't work for everything here, though. It'll just give you one of them. If this was an s minus 3 to the 4 downstairs, you would start with a over s minus 3 plus b over s minus 3 squared plus c over s minus 3 cubed plus d over s minus 3 to the 4. And again, the heaviside trick would only get you 1, so you need to multiply everything out and equate coefficients to get the rest. So I can send you some resources for partial fractions if you would like those. I don't remember if I have them up in the modules already, but if not, reach out, I'll send you good stuff. So from here, the inverse Laplace transform of 2s plus 5 over s minus 3 squared would be equal to 2 times the inverse Laplace transform of 1 over s minus 3, which we know, plus 11 times the inverse Laplace transform of 1 over s minus 3 squared. So here I'm using the linearity of the inverse transform and my partial fractions. So if this thing is equal to this stuff, then the inverse Laplace transform of this thing is equal to the inverse Laplace transform of this stuff. And by linearity, I can split it up over addition. So I take the inverse Laplace transform of this plus the inverse Laplace transform of this. And then from the first guy, I pop out the constant 2. From the second, I pop out the constant 11. Take a second. Questions up to here? Okay. This first piece is what? 2 times, what is the inverse Laplace transform of 1 over s minus 3? What is this, the Laplace transform of?
E to the 3t.
Very good. All right, remember the Laplace transform of e to the at is 1 over s minus a. So the inverse Laplace transform of 1 over s minus 3 is e to the 3t. And then I'll have plus 11 times. I need the inverse Laplace transform of 1 over s minus 3 squared. And here what you should be thinking of is whose Laplace transform looks like 1 over s squared, right? So pretend the 3 isn't here. What's the inverse Laplace transform of 1 over s squared on its own?
That's t.
I heard it. Yeah, t, right? The Laplace transform of t to the 1 would be 1 factorial over s squared. So the inverse Laplace transform of 1 over s squared is just t. So if I apply my exponential shift theorem to this, here it is. I'm going to have it down here. This guy is like the Laplace transform of t, except it's been shifted to the right by 3 units. So the inverse Laplace transform of this, my little f of t is t, and my exponential is e to the 3t. This would be 11 times e to the 3t times t. In other words, factoring out e to the 3t, you get 2 plus 11t left over. So that would be the inverse Laplace transform of this function. It's a little tricky. Like I said, not the simplest thing in the world, Kitty, no. Stay down. Not the simplest thing in the world, but also it's not super overwhelming. It does require you to be comfortable with the basic Laplace transforms. But so does all of your homework from last week, where you're solving differential equations with the Laplace transform. So hopefully those basic Laplace transforms from your table you are comfy with. Those are t to the n, e to the at, and then sine kt and cos kt. Got to be comfy with all those. And then from there, it really is just an application of this theorem. So if you see something like this, 1 over s minus something all to a power, and you need to inverse Laplace transform that, don't think exponential right away. Think power function right away, because it's really like a power function's Laplace transform that's been shifted. And then the thing that makes the shift happen in the Laplace transform is multiplying by the exponential. Let's do one more, then we're going to solve a differential equation with this stuff, okay? Questions on this example? And this one's a little tough at first. Okay, here we go. This next one's a little bit long. I'll get started on the second half of this page, but we'll likely need more space. I want to find the inverse Laplace transform of the following. S over 2 plus 5/3. Again, S's here will have tails. Divided by s squared plus 4s plus 6. A little bit gnarly, but certainly something that could show up. All right, transform both sides of an equation, solve for y of s. You end up with this thing times y of s on the left-hand side. And on the right-hand side, you end up with this stuff coming from your initial conditions. Totally possible. We need to factor the bottom and set up some partial fractions, of course, just like normal. The bottom here doesn't factor nicely. S squared plus 4s. No. This is not a kitty. She's a terrorist. For being a terrorist. Yeah. 6. If you try to compute the discriminant there, b squared minus 4ac, you get 16 minus 24, which is negative. So this doesn't factor. But if you complete the square, you can rewrite this as s squared plus 4s plus 2 plus, plus 4 plus 2, which is s plus 2 squared plus 2. So the bottom we're thinking of like this, which looks like a shifted sine or cosine thing, depending on which piece of the top you take with it. Now, here's the game. Let me come down here. s over 2 plus 5/3 divided by s plus 2 squared plus 2. I want to take this piece over this denominator, and I can treat that as the Laplace transform of a sine. I'll have to do some fudging with constants to make that work. The other thing I want to do is rewrite the s piece here as an s plus 2. Because remember, the Laplace transform of cosine is s over s squared plus k squared. So if I'm going to take this piece over this and treat it as a shifted cosine Laplace transform, I need the variable pieces to match, right? If it's an s plus 2 downstairs, I need an s plus 2 upstairs. Okay. No kidding. No kidding. So the first thing I'm going to do is see what's necessary to rewrite this as an s plus 2. S over 2 plus 5 over 3. Easiest way to do that is to write s plus 2 minus 2 over 2 plus 5 over 3. This is a trick, again, you may have seen in Calc 2, we use this when we're integrating, the add and subtract trick. Again, the goal here is to replace this s over 2 with an s plus 2 over something or times something. I can then split this up as s plus 2 over 2 minus 2 over 2 plus 5 over 3. It's really just arithmetic, but it's fairly sneaky arithmetic. So now I'll have my s plus 2 that I need here to match with this. The other thing, of course, I should combine these terms. So my 5/3 here piece is going to change. So positive 5/3 minus 2/2 or minus 1 is 5/3 minus 3/3. And 2 over 2 is the same as 3 over 3. So this is s plus 2 over 2. I'll write it plus 5/3 minus 1. And then simplifying the fraction there. That's s plus 2 over 2 plus 5/3 minus 3/3 is 2/3. 2/3. So this is some sort of arithmetic or algebra I need to do off to the side before I can get this thing into the form that I need to take its inverse Laplace transform. That means this guy down here is equal to s plus 2 over 2 plus 2/3 all divided by s plus 2 quantity squared plus 2. Okay. So sneaky algebra. Now I can split this up as this over this plus this over this and see what further constant fudging is necessary to get the first to look like a cosine transform and the second to look like a sine transform. So this is 1/2 times parentheses s plus 2 over that denominator. S plus 2 quantity squared plus 2 plus, I don't think I'm going to need any of that stuff, so I'll just write it as 2/3 times 1 over s plus 2 quantity squared plus 2. Okay. So I'm just taking this over this, that's this, plus this over this, and that's this. Now the 1/2 can come out from the first guy. And the 2/3 I already popped out from the second guy. And now, just like we did before, in order to conjure up the inverse Laplace transform of each of these, I should think about the associated non-shifted Laplace transforms. Recall that the inverse Laplace transform of S over of S over S squared plus 2 would be something, and the inverse Laplace transform of 1 over S squared plus 2 would be something. And you got to think a little bit more carefully about the second one than the first. So what's the first one there?
Cosine.
Cosine of what?
Cosine of 2t.
Not quite, very, very close. If this was a 4, then that would be the cosine of 2t. Remember, S over S squared plus K squared or plus A squared, the square of the,
Square root of 2.
yeah, okay, so this is cos of root 2t. And that's the guy I'm going to need to get this, right? This will just be the exponential shift rule together with this. So that would be e to the negative 2t times cos root 2t, and then the 1/2 comes along for the ride. What about the bottom one? This one requires a little bit more work.
1 over square root of 2 sine of square root of 2t.
Very good. Yeah, the way we get around this is by kind of sticking a 1 over root 2 out here and a root 2 here, multiply and divide by root 2. So now this is like k over s squared plus k squared. And this is, let me do that in a different color so we can see which parts come from where. Okay, so the black terms here cancel, right? So this really is the Laplace transform of 1 over s squared plus 2. And that means since the inside thing now I recognize as the Laplace transform of sine root 2t, this is going to be 1 over root 2 times the sine of root 2t. So a little tricky, but not impossible. Now we have everything we need. Go. So the function whose inverse Laplace transform I want, so therefore the inverse Laplace transform of this thing, which remember was s over 2 plus 5/3 divided by s squared plus 4s plus 6 is equal to the inverse Laplace transform, I'll say 1/2 inverse Laplace transform of s plus 2 over s plus 2 squared plus 2 plus 2/3 inverse Laplace transform of s plus 2 squared plus 2. And then each one of those we'll get using our exponential shift theorem and the orange statement on the right. So again, here a is -2 and your well f of t would be this guy, the cos of root 2t. And over here, a is again -2, and your little f of t would be this guy 1 over root 2 times the sine of root 2t. So we see that the first piece here, ignoring that 1/2, this piece, based on these things, would be e to the negative 2t cos square root 2t. And over here, this guy, according to the theorem, would be e to the negative 2t times 1 over root 2 sine root 2t. And that's it. That's the magic. Bringing the appropriate constants along for the ride, we get 1/2 e to the negative 2t times the cosine of the square root of 2t plus 2/3 times 1 over the square root of 2 e to the negative 2t sine of the square root of 2t. I'm sure you can clean up the constants in the second term. This is, we've got a root 2 upstairs and a root 2 downstairs. That's the same as just having a root 2 upstairs, but I'll leave it like this for now. This is fine. Okay, and we've seen plenty of differential equations that have solutions which look like this. And normally, remember how unpleasant it is to get these solutions? Normally, you have to put together your undetermined coefficients business. Building your ODE is going to mean lots of nasty product and chain rule derivatives. And then solving for those coefficients is going to mean lots of work with linear systems. It's a non-trivial affair to get this as a particular solution, whatever, from your work with the undetermined coefficients technique. And it is really a particular solution. I want you to remember that too. When we take the Laplace transform of both sides in these equations, there's almost always a non-zero right-hand side. That's the magic. So it's not just like these are the terms you would get from your homogeneous equation. These are really the full thing. Your homogeneous together with your particular with all the constants thrown in, and then plugging in your initial values to find the values of those constants. This does all of it at once. And that's why people are so into the Laplace transform. All right, we've done a few examples of each of these, but we haven't solved a differential equation yet. And of course, I would be doing you a horrible disservice if I didn't show you how to solve a differential equation at least once with one of these. So questions on this last example here. Feeling okay? All right, let's solve a differential equation. Solve a fresh page. Let's solve. Of course, it has to be an initial value problem, right? Y double prime minus 6y prime plus 9y equals something annoying like t squared e to the 3t. Yeah, 3t. With the initial conditions that y of 0 is 2. And y primed of 0 is 17. Okay, so remember, if you wanted to do this normally, you would, find your auxiliary polynomial, find its roots. That would give you your two solutions, y1, y2, to the associated homogeneous equation. Then you would have to assume from this right-hand side that your particular solution is of the form ax squared or at squared plus bt plus c times e to the 3t. And that assumes no overlap between those, but I think you're good there. And then, oh, actually, there might be some overlap here. Yeah, because this would have a repeated root. Oof, nasty. So your particular solution would be even gnarlier. You'd have to assume a general cubic polynomial times e to the 3t, and then build your ODE, require lots of product rule derivatives, and then solve for those missing coefficients, and then plug in your initial conditions, then build another system to solve for the C1, C2. Fucking nightmare. However, if you begin by taking the Laplace transform of both sides, start by applying L to both sides. On the left-hand side, the Laplace transform of y double prime is s squared times y of s minus s times, little y of 0 minus y prime of 0. And then you have minus 6 times s y of s minus y of 0. And then plus 9 copies of the Laplace transform of little y, which is y of s, 9 y of s, equals the Laplace transform of the right-hand side. So here's a case where we can use our exponential shift rule in the forward direction. What is the Laplace transform of t squared times e to the 3t? Which piece should we be thinking of for the sort of overall shape of the Laplace transform? The t squared or the e to the 3t?
The t squared.
The t squared. Very good, right? This is going to shift my t squared transform. So what's the Laplace transform of t squared?
Two over s cubed.
Very good, right? It's n factorial over s to the n plus 1. So the Laplace transform of t squared, I'll write it in here. The Laplace transform of t squared is 2 factorial over s to the 2 plus 1, which is 2 over s cubed. So the Laplace transform of t squared e to the 3t is this, but with s swapped for s minus 2. Again, just this theorem. Just this theorem. So little f of t here is t squared. And the Laplace transform of t squared is 2 over s cubed. So the Laplace transform of e to the 3t times t squared, a here is 3, would be 2 over s minus 3 cubed. And right away, you see your partial fractions is going to involve some pretty gnarly stuff because you have this repeated factor. It's repeated thrice. Okay. Saving you some algebra, I'll tell you that if you clean all of this up, you plug in the appropriate bits like y of 0. This is 2. Y prime of 0. This is 17, distributing the minus 6. The y of 0 here. Again, 2. If you clean all this up, push all the constants to the right-hand side, you'll get s minus 3 quantity squared times capital Y of s is equal to, pull all the other terms to the right, all the terms that didn't have a capital Y to the right, stuff that's going to be left over, you're going to have 2s plus 5 plus this term, 2 over s minus 3 squared, cubed, sorry, yeah. I'm just taking my notes. So again, just plugging in, putting the y of s's together, putting everything that doesn't have a y of s on the other side, factoring the polynomial that's in front of y of s into s minus 3 squared. Now you need to divide both sides by this and have a common denominator over here. Now, it's actually advantageous to not have the common denominator at this step. I'll show you why. So if I divide through by my s minus 3 squared, I get y of s equals, I'll just divide each term by that. So 2s divided by s minus 3 squared. Oh, no, we're going to have to do it. Okay. Let's just do it. So this is 2s plus 5 over s minus 3 squared plus 2 over s minus 3 cubed. All right. I know how to take the inverse Laplace transform of this now. Oh, sorry. That's going to be to the 5th power now. Sorry, 5th. Yeah. I know how to take the inverse Laplace transform of this, though. This is something I know how to handle. To take the inverse Laplace transform of this, I would want to run some partial fractions. So because the degree of the bottom is strictly larger than the degree of the top, and because as is, I can't find the inverse Laplace transform of s over s minus 3 squared. That's not something I can do. I know that this piece through PFD, so we run PFD on 2s plus 5 over s minus 3 squared to get two s plus 5 over s minus 3 squared equals, and again, the details of the partial fractions I'm going to leave to you. It's 2 over s minus 3 plus 11 over s minus 3 squared. So again, just remember ask yourself, what would I do if I was trying to integrate this? What if this was Calc 2 and I needed to calculate the integral of this? The answer is partial fractions. So here you do partial fractions. The PFD is not bad. The setup, because this is a square, you would get, constant over the first plus constant over the second. And you solve for those constants using combination of the Heaviside cover-up trick and equating coefficients. That means my y of s is equal to this, which is these two, which now just have constants upstairs, so I can find the inverse Laplace transform of those easily, plus this guy, 2 over s minus 3 to the 5. And I want to say again, we don't want to have a common denominator here and then run partial fractions. Your common denominator would be s minus 3 to the 5, and that would make your PFD much worse, right? Instead of just having to decompose something like this, you'd have to decompose something with a power of 5 downstairs. The reason we don't need to run PFD on this piece is because his numerator is just a constant. So if you were to run the PFD on that, you'd find all the terms are 0 except for the constant over s minus 3 to the 5. So there's no need to run PFD on this because we can find the inverse Laplace transform of it on its own. And running PFD on it wouldn't yield anything. It can't be decomposed any further than that. There's no need for it. On the other hand, here you do need the partial fractions because there's no nice way to split this up into pieces that we recognize the Laplace transform of, or inverse Laplace transform of. If it was just 5 over s minus 3 squared, we'd be Gucci. But with the 2s, specifically the s over s minus 3 squared, that's no good. Questions so far? There are very fast ways to get these PFDs done. Hopefully it's something you've practiced in the past. If not, then I strongly encourage you to practice it. From here, I take the inverse Laplace transform of both sides and I get my solution. capital Y of t, my solution is going to be 2 times the inverse Laplace transform of 1 over s minus 3 plus 11 times the inverse Laplace transform of 1 over quantity s minus 3 squared plus 2 times the inverse Laplace transform of 1 over quantity s minus 3 to the 5th power. All right, what's the first guy? What is the inverse Laplace transform of 1 over s minus 3?
e to the 3t.
Very good. So this is 2 times e to the 3t. And then I'll have plus 11 times inverse Laplace transform of 1 over s minus 3 squared. That's one we may want to think about a little more.
T e to the 3t.
Oh, I'm sorry, I was a little bit distracted. Yes, so 1 over s squared is the Laplace transform of t. So this is, let me I'm going to take here the inverse Laplace transform of 1 over s squared on its own would just be t. So this is the shifted version of that, which means my inverse Laplace transform is going to be e to the 3t times t, or t e to the 3t. And I think that's what you said there. And then finally, we have plus 2 times the inverse Laplace transform of this guy. So again, we want to think, okay, well, what's the inverse Laplace transform of 1 over s to the 5? And here we need to do a little bit of that same constant fudging. One over s to the 5 is related to the Laplace transform of what function? I heard something from Maylin, but I think it cut out. What power of t? Remember, when you transform t to the n, you get n factorial over t to the n plus 1.
T to the 4 divided by 4 minus.
So the big thing I'm looking for there is t to the 4, right? 1 over s to the 5 modulo some multiplicative constants is the Laplace transform of t to the 4. So here's what I'm going to do. I'm going to divide by 4 factorial, and again, I'll do this in. So we can kind of contrast and multiply by 4 factorial. All right, now the inside here is actually the Laplace transform of t to the 4. So this is 1 over 4 factorial times t to the 4. Is everybody comfy with that trick I'm using where I multiply and divide by a constant? Has anybody feeling a little bit uncomfortable with that? Want to talk about it more? Okay, so then this is the shifted version of that, shifted by e to the 3t, or shifted to the right 3 units in the s space. So this would be 2 times 1 over 4 factorial times t to the 4 times e to the 3t. And remember what we said? That let me pause for a minute here. Here's your answer. Should put this in black. I'm sorry. All right, here's your answer. Now we can clean it up. 4 factorial, we can calculate that. That's 24. pull down here and zoom out just a tiny bit. Remember what we said at the start about how the associated particular solution here, because this is a t squared, e to the 3t would be kind of most naively, your first guess would be a general quadratic times e to the 3t. And then I saw this. I saw that this has a root of 3, right? The auxiliary polynomial there has a root 3, but it's not just that. It's actually a double root at 3, which means that your right-hand side is not only included in your complementary solution, but because the complementary solution has that double root, the auxiliary polynomial has that double root, you need to stack on powers of t until you become linearly independent, until your assumed particular solution associated with this is linearly independent from the complementary solutions coming from that auxiliary polynomial. Now the auxiliary polynomial there is m minus 3 quantity squared. So you already had a double root there. So your complementary solutions would be like e to the 3t, t e to the 3t. And then you would, in order to stack up and get this to be linearly independent from any of those, you wouldn't just need a general cubic polynomial times e to the 3t, you need a generic 4th degree polynomial, which means you'd have 5 constants to sort out, which means your linear system would be a 5 by 5 linear system to solve for those. Fuck that shit. No way. No way. No way am I doing that by hand. Computer, sure, but by hand, hell no. But look at this. This ain't bad at all. This ain't bad at all. And even without remembering the bizarre multiplication rules associated with repeated roots or the tricks for building up to linear independent solutions when you're running your trial solutions for undetermined coefficients, without remembering any of that bullshit, you get your whole solution right here. Okay, this piece is definitely coming from the particular solution. So you would have found that of those 5 constants, 4 of them were 0. That would be annoying. And these pieces are coming from your complementary solution. So you'd solve one 2 by 2 system to get the 2 and the 11 here. You'd have to solve a 5 by 5 system to get all of those guys to find that all those 5 coefficients associated with a particular solution are 0. And even that is assuming that you remember the right kind of trial solution, which is challenging on its own. Annihilator operators could work here, but you still have to solve the 5 by 5. That would get you around the memorization portion. You got to remember the appropriate annihilator operator, but still not pleasant. Not pleasant. Laplace transform much better. Now 4 factorial is 24. This is 2 over 24, so it's a 12. So this is 2 e to the 3t plus 11t e to the 3t plus 112 t to the 4 e to the 3t. And I hope you see why this is so much nicer. Questions on this? All right, good news from my wife. All right. I am hiding some work here, right? I'm hiding the partial fractions work, but it really wasn't that bad. It's really not that bad. This term makes us scared to think, oh shit, we're gonna have to do some partial fractions like that is large. But we didn't have to PFD this. We only had to PFD this. And that's kind of where we're getting around things, right? If we had to PFD something like this, then you'd have a 5 by 5 system again, and it would be every bit as nasty as the undetermined coefficients method. But because of the linearity of the Laplace transform, and particularly the linearity of its inverse, we don't have to do that. Only had to split up this guy.
Professor, if you were to, for the 2s plus 5 over s minus 3 squared, if you were to like split the 5 to something separate,
I think I need you to move closer to the microphone. I'm sorry, I couldn't hear you.
if you were to split the 2s plus 5 into 2 separate terms, would you be able to do just the PFD of the 2s term? And then like the 5 over s minus 3 squared would be?
You could. But when you do the PFD on the 2s over s minus 3 squared term, you're going to get a constant over s minus 3 squared that you would then want to recombine with the 5 over s minus 3 squared. That's this. So yeah, if you just did the PFD on 2s over s minus 3 squared, you would get 2 over s minus 3 and then 6 over s minus 3 squared, which you would put together with the 5 over s minus 3 squared to yield this. It's not any faster, I guess is what I'm saying. If you're going to do PFD on 2s over s minus 3 squared, that's a 2-term partial fraction setup. And 2s plus 5 over s minus 3 squared is also a 2-term partial fraction setup. It's really not any faster. But
Okay,
yes,
thank you.
yeah, if you were following your nose and you did that, it would work out. It would work out. It just wouldn't save any time. Other questions on this? That's a really good question there from Rob. Other questions on this? Oh, I see there's something in the chat. Laplace is indeed love. Yes. Yes, integral transforms are the shit. I have one other example that I want to work for you guys. I'm going to try to do it a little bit more quickly because I do need to talk about convolutions. Okay, one more IVP. So we're going to solve y double prime plus 4y prime plus 6y is equal to 1 plus e to the negative t, subject to y of 0 equals 0 and y prime of 0 equals 0. And these sort of initial conditions, by the way, are exactly what you do when you're not given initial conditions, but you want to use the Laplace transform. You just bullshit them. Just make everything 0. All right, applying the Laplace transform to both sides. I'm going to jump down to the result. You're going to get s squared plus 4s plus 6 times capital Y of s is equal to Laplace transform over here is 1 over s plus 1 over s plus 1. You put those together and you get 2s plus 1 over s times s plus 1. And then you divide. Y of s is 2s plus 1 over s times s plus 1 times s squared plus 4s plus 6. And the s squared plus 4s plus 6 we've seen previously is an irreducible quadratic. So we run some PFD. And there's no getting around the PFD here. It's a little gnarly. It's going to be a 4-term PFD because the degree of the denominator is 4. You're going to get 1/6 over s plus 1/3 over s plus 1 plus s over 2 plus 5/3 divided by s squared plus 4s plus 6. And this is why we did the other example earlier, because I know the inverse Laplace transform of this is sort of the hard part. So y of t is the inverse Laplace transform. Also, I'll put the 1/6 inverse Laplace transform of 1 over s plus 1/3 inverse Laplace transform of 1 over s plus 1. And then I'll just write this as the inverse Laplace transform of what it is, s over 2 plus 1/3 divided by, remember how we did this? We rewrote the bottom as s plus 2 squared plus 2. So that far right term is one that we calculated earlier as an example. These two we still need to do. So this is 1/6. What's the inverse Laplace transform of 1 over s?
One.
Yeah, 1. 1/6. I'll just leave the 1/6 as 1/6 plus 1/3 times the inverse Laplace transform of 1 over s plus 1. Who is that?
E to the negative t.
Very good. E to the negative 1t, or just e to the negative t. And then the remaining piece here is the gnarly inverse Laplace transform we calculated a minute ago. Let me see if I still have that. I think it's under here. Nope. I moved it. Here he is. So the lingering piece on the side here, don't copy this into your notes right now. This is here from before, so just you would turn back to your notes, but I'll show it here. The inverse Laplace transform of s over 2 plus 5/3 divided by s squared plus 4s plus 6. This thing is 1/2 e to the negative 2t. 1/2 e to the negative 2t times the cosine of the square root of 2 times t. Plus 2/3 times 1 over root 2, which is root 2 over 3, times e to the negative 2t times the sine of the square root of 2 times t. This is coming from previous examples. The other two are easy. Okay. Not bad, man. Not bad. So that's most of the story with Laplace transforms. Most of it. There is one big thing missing, though. So we've got one big lingering question. And I got to think of how I want to write this. I'll say it's somewhat apparent that the Laplace transform of the product is not equal to the product of Laplace transforms. I'll let you check if it's not obvious to you. This would be the integral from 0 to infinity of g of t times f of t times e to the negative st. And this would be integral 0 to infinity g of t e to the negative st. This would be integral 0 to infinity f of t e to the negative st. Even if you know enough higher dimensional integration theory to take the product of two integrals here and try to rewrite it as a double integral, you'll see very quickly that it's not what you get from this, because you have two e to the st terms that don't play nice, and then also you're integrating over a rectangular region. That's a Calc 3 thing. If you haven't got Calc 3, don't worry about it. On the other hand, if you take this guy and you try to apply some clever integration by parts or algebra tricks, you'll discover very quickly that there's no nice way to split that up as a product of two integrals. Again, even if you know appropriate iterated integral mechanisms. So the big lingering question is, what does give you this? Or is there a nice way to think about this? And it turns out that there is an answer here that is somewhat satisfying. So I'd like to share that with you. This is actually sort of the big payoff when you study Laplace transforms from a slightly more grown-up perspective. Now, the notation here is, as used in your book, is perhaps a little bit scary. So rather than trying to scare you, let me give you the answer first. All right, let me show you sort of, so the question here is, well, is there any nice thing which does give this, the product of the Laplace transforms? And the answer is yes. It's called convolution. So you can imagine, you run through your IBP taking Laplace transform, solving for y of s. And on your right-hand side, for whatever reason, you've got a product of functions that you don't want to or cannot decompose through partial fractions. Either it's not a rational function, this is hypothetically possible, or your input, your driver function, your function on the right-hand side is fucked up to a point where the Laplace transform of it is a nasty thing, not one of the nice ones we've done. Particularly here within the unit step functions and the Dirac delta function, because those show up in applications quite a bit. Yeah, the answer here is convolution. So the notation for that is usually an asterisk. The theorem, before I give you the definition of a convolution, I'm going to show you what the result is. Think of this as weird multiplication. Here's a funky multiplication that does the thing. The Laplace transform of the funky multiplication is actually equal to the regular multiplication of the Laplace transforms. So regular multiplication inside equals regular multiplication outside doesn't work. Funky multiplication inside to regular multiplication outside does work. This, in a very deep way, tells us a lot about the Laplace transform. But before I can even hint at why that's deep, I got to tell you what this thing is. All right, so that's, people talk about convolution and they never understand where it comes from or why it's a thing. Admittedly, I did not. When I learned about differential equations, I was like, what the fuck is the star? I'm exhausted. It's the end of the semester. Please, 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 no more. The reason this is a big deal is because it's the operation that you can do between two functions that gives you the product of their Laplace transforms on the outside. So often we want to split up Laplace transforms. That would be nice. It's very tempting when you're taking the Laplace transform of a big messy function to say, oh, I'll just transform the one, transform the other, and then multiply them. Yay. Doesn't work though. It's a linear operator, but it's not a multiplicative operator. So mathematicians go looking for an operation you can do between two functions such that when transformed, you get the product of the transforms. And that's what convolution is. Where f star g is the convolution of f and g. So this is going to be a new function. Let me emphasize the notation here. This is going to be a function of t. So f star g of t, right? It's something you're going to take the Laplace transform of, so it should be a function of t, is equal to the integral from 0 to t of f of z times g of t minus z dz. And this is an interesting operation. It is like a multiplication thing, right? I'm multiplying f times g inside this integral. F is evaluated at z, so z is just some number between 0 and t. And g is evaluated at t minus z, so it's sort of a symmetric thing. So this is the operation. It turns out to be a special form of something called an inner product. Again, lots of deep linear algebra underneath here. Special form of an inner product that behaves nicely with respect to the Laplace transform. I'll tell you here. In your homework, I do ask you to calculate some convolutions and Laplace products, things that look like the left-hand side here. But not by calculating this directly, by using the theorem to say, oh, well, the transform of the convolution is the product of the transforms, and then little f and little g are going to be functions that you know. I ask you to do some similar things with inverse transforms, but again, you're meant to use this theorem. Very rarely will I ask you, probably, I think never, do I ask you to raw calculate this thing, and it's not bad, just to be clear. Let me just do one example. Let's calculate. So the theorem, I'm not going to prove the theorem. Theorem's hard to prove. Requires iterated integrals. Those of you who've had Calc 3, it's not beyond you. But if you haven't had Calc 3 and the tools needed to talk about iterated integrals, even in the improper sense, you know, both of them running from 0 to infinity, it's not going to do it. Let's find this convolution. E to the t convoluted with sine t. So this is like my f. This is like my g. And if we just follow the definition, remember f star g of t is the integral from 0 to t of f of z times g of t minus z dz. We'll see here that this is going to be the integral from 0 to t f of z. If f of t is e to the t, then f of z is e to the z. And g of t minus z is going to be the sine of t minus z, and the integral is done dz. Now this integral requires 2 runs of IBP. This is not the nicest integral in the world. Or you can attack it with complex exponentials. So it's a looping integral if you do it the Calc 2 way. If you do it the way we did when we found the Laplace transform of sine and cosine, you just write sine as a complex exponential, or the imaginary part of the complex exponential. The integral is not the end of the world, but what we're going to get out, if you remember your looping integral as well, is 1/2 times e to the z times the sine of this thing, sine of t minus z, plus e to the z times the cosine of that thing, cosine of t minus z. And we would have to evaluate this from z equals 0 up to z equals t. So remember how those looping integrals work. You run IBP twice, the original integral shows back up, you add it over to the other side, you get 2 times the original integral, you divide both sides by 2, you get this. And then you just evaluate between your bounds. I'm writing z equals 0, z equals t here, because there's lots of variables. I just want to remind you, what's what. When we plug in 0 for z, this becomes 1, this becomes 1, this becomes sine t, this becomes cos t. So you start off with 1/2 sine t plus cos t. And then when you plug in z equals t, this becomes the sine of 0, this becomes the cos of 0. So if you rearrange all the terms, you'll get 1/2 negative sine t, that's coming from the 0, minus cos t, right? So you'd have this plus this, but it's at the bottom end, so you subtract it. And then at the upper end, when you plug in z equals t, this goes away, it's 0. And this becomes cos of 0, which is 1. So you'll just get e to the z, but with t plugged in, so plus e to the t. So that is the convolution of these functions. If you convolute e to the t and sine t, you get 1/2 times negative sine t minus cos t plus e to the t. Is there a way I could use this? Remember what our convolution theorem says. It says that the Laplace transform of this convolution is the product of the Laplace transforms. So one thing we could say here, how do I want to say this? Yeah, we could say it like this. I don't like the way your book does this. Here's how you would actually use this. So recall that the Laplace transform of f star g is the product of the Laplace transforms. I'll write it as capital F of s times capital G of s. So if I wanted to take the Laplace transform of this convolution, then I could just multiply the Laplace transforms of e to the t and sine t, respectively. So I could say find the Laplace transform of e to the t starred with sine of t without calculating the inside thing, without calculating e to the t starred with sine t. Now we already do have e to the t starred with sine t, that's this. So I could, if I wanted to, take the Laplace transform of this, and that would give me what I'm after. Or I could use the theorem. By the convolution theorem, the Laplace transform of e to the t starred with sine t is the product of the Laplace transform of e to the t with the Laplace transform of sine t. And then the Laplace transform of e to the t, I know that. What's the Laplace transform of e to the t? Just regular forward Laplace transform.
1 over s minus 1.
Very good. This is 1 over s minus 1. And the Laplace transform of sine t?
1 over s squared minus s or plus 1. I forgot.
So yeah, the sign is 1 over s squared plus the inside number squared. So this would just be s squared plus 1. Okay, in other words, the Laplace transform of this convolution is 1 over s minus 1 times s squared plus 1. So here's one power of the convolution thing. It's a contrived thing, right? Nobody would ever say, like, for some reason, I need the Laplace transform of the convolution here. But if you wanted to take the inverse Laplace transform of this, but really didn't want to do the partial fractions, you could calculate the inverse Laplace transform of this as the convolution of those two functions. That's one approach. Another thing is that you can find inverse Laplace transforms. Let's see. Maybe I'll just leave it at this. Yeah, probably better not to beat you to death with convolution. Yeah, we're out of time anyway. Okay, so that's where I'm going to leave it. The definition of the convolution function, or the definition of the convolution operation, it's a little bit weird. It's a little bit wonky, but you can calculate it. It's not terribly bad. Calculating Laplace transforms of convolutions, very nice. Laplace transform of the convolution is the product of the Laplace transforms. The reason this shit matters so much is because the unit impulse function is a convolution. And the way we use the Dirac delta function is as a convolution. So maybe in passing, this is a silly example, but why this stuff matters. I'm not going to test you on it, but I can't let you go without at least telling you why this matters. Two of the most important, so why shit matters. Aside from the sines, cosines, exponentials, and polynomials that we've been dealing with as input functions, there are two very important input functions. One is called the delta function. It's really not a function. You can say that delta of t is equal to 0 if t is not equal to 0, and it's equal to plus infinity if t is equal to 0, and has this property that the integral from negative infinity to infinity of f of t times delta of t dt always plucks out f of 0. Or more generally, so much shit to say here, that delta, the integral from negative infinity to infinity of delta of t dt, this is always 1. So these kind of three things are a nice way to think about it. It's what's called a distribution function. It's really not a function because it doesn't take a nice defined value at 0. It jumps up to plus infinity. You kind of think of it as a limit of bell curves where the curves get taller and narrower. And if you want to pluck out a particular function value from an integral, I would integrate that function against delta of t minus a dt. This will always give me f of a. So kind of what the delta function does is it lets you pluck out or sieve for function values. You know what a sieve is, like a colander? If you want to sieve for the function values of f of t as a product of integrals, or as an integral of a product, the delta function is the kernel that lets you do that. You might recognize this as looking very much like a convolution, and it is. And that's why convolution is so important in differential equations. This is your unit impulse function, right? If I want to kick my system, like I've got a spring mass dashpot system or some physical system that I want to kick with a force of 1, or if I've got a circuit that I want to hit with a pulse of current, then the delta function is kind of the natural mathematical object for doing that, but it's very weirdly defined. It interacts very nicely, though, with this like convolution operation, in that it just picks out that one function value. So this is the first very important input function in application problems, real world problems, which are just barely beyond the scope of this course. Almost to a place where we could do it, but I would need another 4 weeks. The other one, your book calls the unit step function, u of t. And this guy, what he does is he's equal to 0. And then he jumps up to being equal to 1. And then he jumps back down. His graph looks like this. Both of these have that feature that the area underneath them from -infinity to infinity is always 1. This guy kind of is, if you want to input a force for a particular little bit of time, and there are other definitions of the unit step function. Let me actually, it does vary. This one is here. This one is the one that I think of when I think of these things. The one your book uses is defined piecewise to be 0 if t is less than 0, and 1 if t is greater than 0. So his graph would actually look like this. And this has some other nice features. Like if you want something to turn on at a moment and stay on, like your circuit, you flip a switch and then that switch stays on. And then you've got your other driver function, like your sinusoidal input current. If you want to model what would happen if, rather than assuming that system has always had the current running through it, you want to see how the system, the circuit would respond when you turn on that current and then leave it on. You would multiply your sinusoidal input by this guy. And just like you can kind of shift that rule for the delta function, you can shift this guy. This is 0 if t is less than a, and 1 if t is greater than or equal to a. And that shifted version, it looks how you would think it looks. Rather than turning on at time equals 0, he turns on at time equals a, and then just stays up here at 1 forever. The Dirac delta function really doesn't have a graph. I can try to show you something really quick. But the Dirac delta function, you think of it as like these peaks, like a bell curve, but it's a limit of bell curves that get narrower and narrower and taller and taller. That's why you say, it's infinity at 0 and it's 0 everywhere else. It's a very weird function, technically not a function. But these are two different things that you would multiply your input function by. So your g of x or g of t, the right-hand side, that's the driver, remember, or the input in the application problems. That's what tells you kind of, it's what tells you how you're molesting the system, right? Like the current you're feeding or the way you're pushing on the mass. Whatever it is, that system at rest maybe isn't very exciting. But if you give it a kick, if you smack it, then it'll start to shake and jiggle or do whatever. Current will run through the circuit. These guys, delta and u, are two ways of kind of turning off and turning on and turning off those inputs. So u has your input off until you get to a certain time, and then it turns it on. And you would just multiply u of t minus a by your normal input function. And that is looking a lot like a convolution, right? Imagine this thing times g of t. Looks like a convolution. Similarly, the delta function, rather than turning on and staying on, it lets your input function do one thing, just one thing. whatever it does at 0, or in this case, whatever your input function does at a. That's the only impulse you're allowed to have. So this is kind of like being struck by lightning. If you got a circuit that's struck by lightning, this is kind of like having your switch turn on. And then those two things are, one, important in applications, and two, when you multiply by your input function, they become convolution type objects. So if you wanted to take your f of t times delta of t minus a and calculate its Laplace transform, that would be a convolution of the delta function with your f of t. So out there in the real world, if you go and take a circuits class or something like that, you will have to deal with those sort of things. And the convolution theorem is everything there, because the Laplace transform of the convolution is easy. But only if you can use that theorem. The raw calculations are incredibly hard. I'm not going to make you do it, but I wanted to show it to you. Next time, power series. Power series is the last thing we got to talk about in this class. Maybe the hardest thing we're going to talk about in this class, depending on how comfy you are with power series material from Calc 2. So your last homeworks are up. You can get started on the power series homework if you want, right? It doesn't, you're not unable to touch that just because we haven't lectured on it. Some of it is just review. So if you're nervous about the power series, I would recommend jumping into it right away. Start the problems that look like stuff you saw in Calc 2 and try to remind yourself how the notation works and what the terminology is like. While you're doing that, of course, finish up the Laplace transform homework. I'll see you guys tomorrow.